And thanks so much for coming.
No, I'm sorry I was running late, but I'm happy to do this. It's always fun.
Cool, and we'll be having dinner after this, so
Great.
if you want to join.
I'll try. Depends.
Yeah, no worries if not, but we definitely feel that we should offer.
Oh, I appreciate it. Of course, yeah. And by the way, so your guys' wrap-up time is before 7, right?
At 7,
like
pretty
25.
cool. All right, I think we've about got stuff. Oh, could you just...
Yeah.
So that we
Also,
can check that it's all working.
Yeah. Also, do you have audio out or?
No.
Okay, cool.
This room is a bit wonky audio, so it's definitely easier to not. All right, all good?
Let me just turn my phone on silent.
Sure.
Do you guys have a slide advance or no?
Hmm?
Do you guys have a slide advance by any chance or no?
I don't think so.
That's fine.
Cool. All right. Next up, we've got MIT professor Max Shulaker here to give a talk about the future of computing, since we've gone over so much history today. So I'll leave it to you.
Appreciate it. Thank you so much. I'll speak without the microphone. Can everyone hear me okay?
You need to in front of
Do I need to? Bummer. Alrighty.
speakers off for you, so you don't have to hear it yourself.
It's okay. Whatever easiest. Alrighty. Let me just move this guy over here then.
You're hooked on the chair.
You can move the microphone over to the table if you like.
It's okay. It's okay. Alrighty, so let me introduce myself a little bit, then I'd like to get to know you guys a little bit better, and then I'll speak about what I think the future of computing will look like. So I'm a professor here at MIT. I'm in my 4th year now. I lead the Novel Electronic Systems Group, or NOVELS for short, and we work on building what we think the next generation computing system might look like. So just a show of hands so I can just get a rough idea, right? So I believe most folks here are MIT alumni, correct? So raise your hand if you're, okay, excellent, terrific. Okay, hold on, raise your hand if you're a current student. Alrighty. Okay, for the folks who used to be here, who was 6'1", by any chance? Okay, 6. Okay, fair enough, okay. 6'2"? Fair enough, so EE and CS, and then more on the CS side. Okay, terrific. Okay. Okay, so I'm a 6'1"er, right? But I think you'll see how this is relevant to all you folks. I should mention I'm a pretty informal guy, so at any time, feel free to interrupt me with questions or comments or whatnot. We can keep this fun. So let me begin with some motivation. So we all know that electronics make the world go around, so to speak, right? And with the exponentially growing availability of big abundant data, which is being generated from these trillions of sensors, which will soon be connected across the Internet of Everything or the cloud, it's obvious that electronics have the potential to continue to have dramatic impacts in all of our lives, right? And these applications range from genomics for personalized healthcare to building smarter cities, to science, finance, security. I mean, the list is literally endless. And while it might seem that such a broad range of applications share very little in common with one another, they actually all share a very important common thread. And you know what that common thread is? Seriously, I'll make this, sorry?
They're all computers.
They're all computers. There's something even more important in common with them. Yes?
Well, more fundamental, transistors, right?
And they're transistors, that's true.
Transistors.
Information. Okay, let me tell you what I think they all have in common today. They're all really hard to do, okay? There's a problem, all right? And the problem that all these applications are facing is that electronics today simply can't keep up with their demands. We're swimming in sensors, drowning in data. There's so much data being generated from such a wide variety of different sources at such a fast pace that electronics today simply cannot keep up. And the reason why electronics cannot keep up with these growing demands of applications is because electronics is not just hitting one problem or two problems. It's that electronics and computing is hitting many walls all at the exact same time. It's the perfect storm. So at the exact time we're demanding the biggest gains of computing, we're hitting all these fundamental limits all simultaneously. So show of hands, raise your hand if you've heard of the power wall, or the end of Moore's law, the end of scaling, right? Perfect. Okay, so everyone, probably familiar with that, okay? So this stems from the fact that as we shrink devices smaller and smaller, they are no longer becoming more and more energy efficient. So that is what we refer to as the power wall. But that's not the only problem. There's the memory wall. So raise your hand if you've heard of the memory wall, the memory logic bandwidth wall. Oh, most folks, okay, good. So the memory wall refers to how a processor today can spend the vast majority of its time and energy just moving data around a system. From your processor to off-chip memory, back to your processor again, back to your memory, the processor, back again. Time, energy wasted not even doing useful computation. So anyone have a guess? If I run some big data analytics on my laptop, what percentage of the time do you think is it computing, and what percentage of the time do you think is moving data around? Anyone have a guess on the breakdown? Yeah. 80% moving data. Worse than that. It's about 95% of the time and energy. Time and 95% of the energy is spent moving data around a system. Okay? Then there's communication wall, the interconnect wall, complexity wall, resiliency wall, and so on and so forth. This list goes on and on forever. So the question is, given all these walls, how can we possibly enable the next generation of computing systems? The future seems pretty bleak. Well, how do we try and improve computing today? Well, today there exist two very separate, disparate approaches. Right? On one hand, we try and create a better switch, a new transistor. Right? This is probably what you thought I was going to say. Right? A whole host of new technologies to choose from here. And while this is important work, it faces some major challenges. Right? So first off, for many of these new technologies, we simply can't build them yet. Right? They only exist on paper. And even if you could build a really great transistor, there's a big disconnect between building a really great transistor and building a working system which has a billion with a B working transistors, all with very little variations, yielding them, et cetera. So actually, I asked this question once to my students, and they didn't know the answer to this. But maybe you folks will. In a chip that has 10 billion transistors, do you know what percentage of them work?
Well, it depends on what day you're talking about, right? They decay over time.
But if we're just looking at it works or it kind of doesn't work, if I had to bin them up. About 25% yield. So this might surprise you. So the yield of the transistor, the devices, at 100%. 100%. Out of those 10 billion transistors, if you have 10 billion and 5 transistors, 10 billion and 5 have to work. And not just work, they all have to match each other. And the yield loss is the yield of an entire die. So the yield of an entire die is, by the way, way more than 25%. We're talking 85, 90, 95% for commercial products. They're yielding 95%, 90% on 10 billion with a B working transistors all flawlessly together. That's how amazing transistors are today. Okay?
Unless it's 10 nanometer Intel.
Nope, even that. That's what they yield today. It really is remarkable. I talk about memories, for instance, in my class a little bit at the end of my Classics 1 2. Do you know how many electrons are stored on a flash, memory cell, like on the floating bit, on the floating gate, to differentiate between a 0 and a 1? Like when you store a 0 and a 1 in your memory. Do you know how many electrons are stored on there?
A few dozen.
A few thousand. So it used to be a few dozen, exactly, a few dozen. And it will keep that there for 10 years or whatever, right? I mean, it's remarkable what devices are today. Anyway, that's a little bit of a tangent, okay? So this is one way how we improve computing. As I mentioned, there's a big challenge in getting them all to work. But there's an even bigger problem here. Because even if you gave me the best transistor in the entire world that you could ever imagine, something that is the best transistor, the fundamental limits, you would still only see limited benefits for a computer. That might seem surprising, but if you think about it, the best transistor in the world would only address the device-level inefficiency in a system today, which is a very small portion of the total system-level inefficiencies. For instance, the best transistor might address the power wall, but it wouldn't do anything to address the memory wall, which I spoke about previously. Right? So a second separate way we try and improve computing is by creating new computing architectures. These range from multiple processing cores, specialized accelerators, ASICs, etc. And while this is also very important work, it too faces challenges. There are only a limited number of design tricks we can play, and we play many of these already. We already have accelerators, we already have ASICs and whatnot. And moreover, leveraging design complexity in order to hide inefficiencies is not a free lunch. Do you guys know what the most expensive part of selling a chip is today, or getting that chip to market is? It's not manufacturing it, it's designing it and verifying it. Because systems are so complex to hide these inefficiencies that it's really hard not to ship a product that doesn't end up getting the blue screen of death or something, right? Clearly, business as usual is insufficient, and something new is required to achieve that next massive gain in computing. And what is required, what I'll be speaking about, is what I like to call nanosystems. Okay? So what exactly is a nanosystem? So let me show you. So a nanosystem is when we start by taking new emerging nanotechnologies. These enable new types of devices, new fabrication techniques, new types of sensors, etc. And only by first overcoming their inherent imperfections, large-scale fabrication, etc., can we then actually make use of these benefits, allowing us to combine them all in order to realize revolutionary new system architectures, which in turn can enable a whole new class of future applications, like big, abundant data applications. Maybe I said something wrong. Kidding. No, I'm kidding. And I always say that while each sphere of work here is important and necessary in its own right, it's only by connecting and combining the right emerging technologies with the right system architectures for the right applications, which allow you to achieve truly massive benefits. Now, this is admittedly abstract, so let me give you a very concrete example of what a nanosystem can look like. So this is what a chip looks like today. So it's two-dimensional. You have your processor, that you can just hold in your hand, your i7 or whatever, and off to the side you have your off-chip memory, and off to the side from that you have your package sensor, like an imager, for instance. And these are all connected with sparse, pin-limited connections, wires you can physically see with your eyes. And this is what a futuristic nanosystem looks like, where we have multiple layers of computing built directly on top of one another, interleaved with layers of memory. You can even add increased functionality like massively parallel sensing directly onto the top layer of this chip, all densely integrated in these 3D stacks through very fine-grained vertical interconnects, truly embodying now computation finally immersed with memory, finally immersed with increased functionality like massively parallel sensing. And the reason why this is a future nanosystem is that while these systems would be nearly impossible, if not completely impossible to build, with today's existing silicon-based technologies, which is what every computer today is made from, today I will show you how by leveraging new emerging technologies that we can actually build these chips today. And I want to be very clear here. When I say that we can build these chips today, I mean that we are actually building these chips today. So this is not a 3D rendered pretty cartoon that I had some student draw up for me. This is actually a 3D rendered graphic of an actual chip that's been designed, manufactured, we have working already today. Okay, so this is very, very real. So let me spend the next 10 minutes or so showing you how we can actually build these future systems and then tell you what we can actually do with them. Some pretty exciting new applications that we can actually do. If we want to begin building these new types of nanosystems, we have to start by using new emerging technologies. And technology which my lab focuses on here at MIT is called carbon nanotubes, or CNTs. So a show of hand, who's heard of a carbon nanotube? Okay, who's heard of using them to build a space elevator to the moon? Okay, well that's not what I'm going to use with them, but it's perpetually on my radar. Okay, you never know. Okay, but this is great. So a carbon nanotube, a little schematic over there on the right, is basically a rolled up sheet of graphene to form a nanocylinder with a diameter of only 1.5 nanometers. So you could fit tens of thousands, 100,000 of them within a single human hair, within the diameter of them. They're extremely, extremely small. And we can use them to build carbon nanotube field effect transistors, or CNFETs, which is the schematic in the middle, which is basically like any existing transistor today. Imagine a silicon transistor. All you do is take out the silicon from the channel of the transistor, replace that with carbon nanotubes, and voila, you have your CNFET. Nothing else in your chip has to change, though it can change if we want it to, and we will want it to. Okay? And over here on the side, you actually see a scanning electron microscopy image. This is the image we take with electrons because it's 500 times smaller than the wavelength of light, so you can't see it with light, but electrons we can see it. And you can see the actual carbon nanotubes. Those are the vertical lines, which are horizontal on our wafer that we build our transistor on top of. Yeah?
For energy efficiency, you say an order of magnitude benefit. Does that mean 1/10 the electricity consumed for the same
Perfect.
function?
Yeah. So the motivation for using CNFETs, there are a couple sources. One of them is this energy efficiency benefit. And whenever we talk about energy efficiency benefit, we need a metric. And the metric that we use is energy delay product. It's called EDP. And what that's a metric of is energy efficiency and speed. because you can always go faster for more energy. You can always save energy by going slower. What you really care about at the end of the day for any application is how fast can you complete it and how much energy did it take. And that's energy delay product. So CNTs give you a 10x benefit in energy delay product. So you can either go 10 times faster for the same energy, you can go the same speed for 10 times less energy, or you can go 3 times faster for 1/3 the energy. Okay, so that's this benefit of 10x. Okay? But that's not all. There are other benefits. You can do new things with these technologies as well, like make a whole bunch of new types of sensors, which I'll be speaking about shortly. Okay, so now that we have our transistor, how do we actually build a computer out of it? Well, I won't go through all the steps of building a computer, but let me show you. This is what the simplest schematic of the simplest possible logic gate is. This is just an inverter. So this is a not function. When you program it, this is what it actually looks like. It has 2 transistors. And the key thing for those of you who are familiar with CMOS and silicon, this is CMOS with carbon nanotubes. Nothing is different. It's the exact same design flow as you design a silicon chip. So someone who's designing circuits doesn't even know they're designing systems with carbon nanotubes now. Okay? If you're not familiar with that, don't worry. I'll never talk about it again. Alrighty. So over the last 10 years or so I've been working on nanotubes for about 12 years. I'm a little older than I look. But for about the last, I guess 20 years now, CNTs have been around. There's been a lot of progress in recent years. So rewind about 15, 20 years ago, and people had made the first transistors using carbon nanotubes. This is work done at the same time at IBM and Delft University. Fast forward a couple years, some work in my own PhD, for instance, was focusing on how do you actually build a system with them? Because when you have all these carbon nanotubes, they're not all perfect. How can you yield 10 billion with a B working carbon nanotube transistors just like we do with silicon? And then fast forward a couple more years, about 5 years ago, we're building very small scale chips, like the first computer made entirely from carbon nanotubes. This was published in Nature about 6 years ago. It had 172 transistors. So if you're ever interested on the smallest possible computer that you can build and still call it a computer, you can read that paper, and that'll actually show you pretty much the smallest computer you could ever build. It's a Turing-complete computer still, but only 172 transistors. So what's happened kind of since the more recent years, we've been spending a lot of time trying to show that we can actually build working computer chips with these new technologies. So just about a year and a half ago, we made the first mixed signal circuits with carbon nanotubes. These had a couple hundred CMFETs. Fast forward, just a couple months, this is about just shy of a year ago, and now we're making these monolithic 3D imagers. So this is an imager which has silicon on the bottom layer for your imager, and then right on the imager itself, we build multiple layers of computing logic. So in real time, your camera underneath captures the image, and then instead of reading out sequentially all the bits, along your, bit lines and word lines, one at a time, instead all the data from all billion pixels in parallel send it data directly vertical up in the stack, which is then computed on by the carbon nanotubes, which then sends all of its data directly vertically up in the stack. So in real time, the output of this camera is no longer RGB pixels of this massive output, but now highly processed information. In this instance, it was edge detection. That's what the camera actually saw, and now we're working on classification. So you take a picture, the camera itself, it outputs classification. It outputs person or dog or something. And this is, if you think about it, this is something that, how this project actually started, was I asked my student, why does a computer run at gigahertz? And why does my camera run at, 20 frames a second or something? It's absurd, right? There's this disconnect of millions. And do you know why cameras are so slow? Because you have to read out the data sequentially because we have 2D chips today. You have your imager here, your processor, you have to read out one at a time. Okay? So we actually are building systems like this. Then we're making memories, so raise your hand if you've heard of SRAM. Perfect, so we've made SRAM arrays with carbon nanotubes. And then this was actually published just like a month ago or so. You might have seen it, it just came out in Nature. So we actually made a RISC-V microprocessor, full 32-bit instruction set, 16-bit data, RISC-V, a processor made entirely using CNFETs. No redundancy, no nothing. You can program it just like you program any kind of RISC-V that you have at home to control a robot, do whatever you want. So we're actually able to build working systems using these new technologies. Okay, so I hope, yeah.
I have a question.
Yeah, of course.
So, I know that you got MIT and Analog Devices. What was that other logo?
DARPA. Yeah, DARPA. So
Analog Devices manufacturing that for you?
So this chip was manufactured here, but at the very end of this, I'll speak about commercialization and how things are actually moving out into the real world now. So without jumping the gun too much, what I will say is for the first time, and what I'll kind of end today with, there's always been this disconnect between, well, actually, let me ask you this. Who has done research in academia before? Okay, most folks. Okay. So let me tell you my experience with the research. This is a little aside. So it was the most exciting time of my life, and it was also the most depressing time of my life doing research, okay? I hear some nervous laughter from some students, yeah. So it's exciting because I really believe what we're doing can change the world, right? But it's depressing because there's such this disconnect between what we think these new projects are going to do, all this research and stuff, and what we actually do, right? So oftentimes I hear technologists speaking about how this new thing's going to change the world, and then I show you a single transistor, which is a glorified light switch, right? So part of our focus is how do we actually turn this stuff into reality. So I'll be speaking about, at the very end of this, we actually lead some of the largest single research programs here in the US. I'm talking 8, 9 digits sort of stuff, $100 million to actually build these chips that you're seeing right here in industry. And I'll kind of wrap up by giving you some ideas of what's happening there.
So that RISC-V picture
Yeah.
doesn't look like a typical CPU. What's going on in there that makes it look so different?
So weird, yeah, good question. So what you're looking at here, can you see the mouse? Yeah, okay, perfect. So this is the actual chip, kind of zoomed in. This is SEM images. There are thousands of them cobbled together so you can actually see it. So here, these are just metal wires and stuff. You don't really see anything. The stuff on the perimeter, these are actual metal pads that come out, which aren't in a typical chip. We have this so that we can actually go in with tiny, microscopic needles to actually probe different areas in the circuit to prove it works. Because if I just programmed this and had it, have it do something, you might say, oh, some of it works, but there's some bug in it somewhere, and if I really exercised it, it wouldn't work. So we proved, that by measuring every possible different transition, et cetera, and all the internal nodes, et cetera, that the RISC worked flawlessly. So that's why it has all the stuff on the peripheral around it. Okay? Yeah.
Can you clarify what you mean by prove? Because that can mean different things between just like running a gigantic test suite
Versus formal verification.
Formal verification.
Okay, yeah.
Okay.
Yeah, so and all the experimental stuff. So yeah, so a whole another bag of worms. I won't get into it now, but yes. Okay. Alrighty. So I hope I've been able to show you that using nanotubes, we can actually build stuff with them. Maybe a 10x benefit from nanotubes doesn't seem crazy. Okay, but I don't want to just work on a 10x benefit. Because if I say 10x, divide by 5 or so, and you're going to be left with 2x, right? I want to get a 1,000x benefit. I want to get a 2,000x benefit. I want to get a 10,000x benefit, right? I want to change the world. That's my goal. So how do we do even better, right? How do we go from a 10x benefit to a 1,000x benefit? So if we want to do even better, if you want to really revolutionize computing, then you need to combine the benefits that you can achieve at the device scale with the benefits you can leverage at the system or architectural level. And that's where 3D integration becomes very important. So there is 3D integration today, and it's done through chip stacking. So this is when you build separate 2D substrates and 2D chips, and then physically stack and glue and bond them on top of one another using through silicon vias or TSVs to connect these different 2D wafers and chips. And these TSVs are very large and very sparse. And that limits the bandwidth that you can send between these chips that you stacked. Now what I'm going to show you experimentally is the dream of 3D, monolithic 3D integration. This is where we can build each of these layers directly on top of one another, all over the same starting substrate. So there's no wafer bonding required here. You simply give me one blank wafer, and I build a chip right on top. I build more, and they're all built right on top of one another. And because of this monolithic integration, I can use my nanoscale intralayer vias, or ILVs, which are already in the metal wires of chips today, to connect all these different vertical layers. And these nanoscale vias are on the order of 50 to 60 nanometers in diameter in today's processing, are orders of magnitude, more than 1,000x denser than TSVs used in chip stacking today. And that means that the bandwidth between these layers can be over 1,000x the bandwidth that you can achieve today between heterogeneous parts of a system. And where I can really leverage this massive increase in connectivity is not just stacking layers of logic on top of logic or computers over computers, but stacking layers of logic on top of memory. Because now this massive increase in vertical connectivity directly translates into an equally large increase in your logic to memory bandwidth, which has serious positive impacts for applications today, both in terms of energy and efficiency. I've listed 3 examples of how so, but by no means is this list anywhere near exhaustive. So first, memory access time is reduced, so your processor spends less time being idle, just waiting to get the data from the memory. And secondly, the memory access energy is also reduced because the memory and logic are placed in such close proximity to one another. And thirdly, the resource contention is also reduced due to the wide connectivity you have between these layers. Now, despite the promise and all the benefits of this 3D integration, there's always a catch, right? If it's too good to be true, it is always too good to be true. And the catch here is that it's very difficult, if not impossible, to build these types of chips today. The processing temperatures in all these upper layers of the circuits has to be very low temperature, below 400 degrees C. If you go above that temperature, you'll melt the bottom layer devices and your metal interconnects. It is a particularly challenge for today's silicon CMOS transistors or regular silicon transistors. Does anyone know how hot it takes to fabricate a silicon transistor? Anyone have a guess? Exactly. It's around 1100, 1200 degrees Celsius to fabricate a silicon transistor. So it's way outside of this limit. By the time you build the next layer of silicon transistors or memories, you melt everything underneath it. So this is where we can really leverage these new emerging technologies, which can be built at very low temperatures. For logic and sensing, we can use carbon nanotubes. Can be fabricated actually at room temperature below 200 degrees C. And for memories, a whole host of new memories to choose from. RRAM, CBRAM, STT-MRAM, all these acronyms for different memories. You choose whatever's best for your specific application. And what I really want to emphasize about this approach is that we really do now get the combined benefits. We're using these energy-efficient, high-performing devices with these energy-efficient, high-performing architectures, which are naturally enabled by using these new devices to begin with. And while this vision is exciting and compelling, the most exciting part of this is that we can actually do it today. It's not just a vision. So this was one of our more recent demonstrations. It's called 3D Nanosystem. It was the first monolithic 3D integrated chip, integrating layers of logic, memory, and sensing. To give you an idea of scale, it has over 2 million carbon nanotube FETs in it, over a megabit of RRAM, one of these new memory technologies, all fabricated in the same kind of 3D chip across 4 different vertical layers with millions of interconnects connecting all the different layers. Again, not a cartoon. We've actually built how this chip working today. And what's inside of it, how do you actually make it? So you start with a bare silicon wafer, just like you make any chip today with. So everything starts the same. And we build the first layer of your computer, just your regular computer chip. And I want to pause here and make 2 very important points. The first is that this bottom layer could be made from silicon today. And actually, we do make it out of silicon. And that's not because we have to. It could be a bottom layer of high-performance logic. We choose to build this out of silicon to explicitly demonstrate for you that everything that you've seen here is not just manufacturable, but also 100% compatible, both in terms of design and processing, with existing silicon infrastructure today. And that compatibility with what exists today, with the billions and decades worth of money and time that's been invested to develop this infrastructure, is so important when considering the adoption of new technologies. I don't care how exciting something is, if it requires building a new fab, that's a $50 billion investment that very few companies in the world, there are 2 in the world, maybe 3 actually, who might be willing to take that risk. Right? So it has to be compatible with what exists today. And this demonstrates that we are. The second point is that the silicon can only be on the bottom layer because it takes such high processing in order to fabricate. So the silicon is just on the bottom layer. Okay, so what do we do next? Well, then you build, just like you do a normal chip, you build your metal wires. So that looks like you put down an insulator, you etch and fill in all these metal wires, and you keep doing this a couple times. And I want to emphasize for you that these ILVs are very dense, nanoscale, because these are the regular metal wires that already exist in your 10 or 7 nanometer node chips that are already being manufactured today. And what we do is we just stop at some point. We stop after building, let's say, the 3rd metal layer, and then instead of building the 4th metal layer, we build our layer of carbon nanotube transistors. So we put another computer right on top of that. And here, the computer can do a couple different things. So first, we build memory access circuitry for layers of memory that we will be building on top shortly. And we also build mini classification accelerators for on-chip embedded computing and machine learning, which I'll speak about shortly. So just keep this in the back of your mind. So what do we do next? We do more amount of wires. We then build a layer of memory using RAM. Here you see a zoomed in SEM showing the crossbar memory array. At the intersection of those lines is where each RAM memory bit is. We then do more amount of wires, and we put on the top layer of the chip another layer of carbon nanotubes. If you zoom in, these are actually 4 inverters. If you zoom in, you can see the carbon nanotubes within one of these transistors in that chip. And we want to go one step further. And to demonstrate the increased functionality that these new technologies can give you, not just transistors, but also sensing, we'll actually functionalize these transistors to make them all different, and actually to make them gas sensors. So actually, we'll make over 1 million unique gas sensors built directly onto the top layer of this chip. And when you take a look at these systems that have millions, in this instance, gas sensors, but any type of sensor, built directly over millions of memory cells, built directly over embedded computing and machine learning, all connected through millions of interconnects. These systems can and do today capture terabytes of information each second from the outside world, store that raw data in on-chip memory, and then process on it in real time, transforming this massive raw data deluge into highly processed, useful information. And let me show you how this chip actually works. As I mentioned, these are not cartoons. These are actual chips that work today. So we take this chip, as I mentioned, we have 1 million gas sensors. So in this instance, it's to smell what's in the ambient. So we put it inside of this vacuum gas chamber, and we can bubble in vapors from whatever liquid that we want it to basically smell. And this is some raw data measured from the chip. 1 pixel is 1 sensor in this 3D stack that's written its value, either a 1 or a 0, into the RAM memory cell built directly underneath it with some carbon nanotube kind of digitization circuitry to digitize it before it writes into the memory cell. A black pixel is if that sensor did not respond strongly to the gas, and a white pixel is if the sensor responded very strongly to the gas. And here I'm showing you just around 2,000 or so of these individual 3D sensor cells. But remember, the chip has over 1 million of them. But just by looking at 2,000, you can already visually see a difference in response between a chip that's exposed to lemon juice or rubbing alcohol vapors. But importantly, this chip doesn't just generate massive amounts of data, it also computes on it with that embedded machine learning, with those classification accelerators I told you about also. So the chip actually computes and actually extracts out features based on the data that it's capturing as well. And here you can see it's calculating 2 different features to use to classify what it's smelling. So you can do PCA analysis on the features that it's basically calculating from what it's sensing. And here you can see the ability for this chip to actually learn to recognize different liquids. So it could learn to smell and distinguish between lemon juice, vinegar, rubbing alcohol, vodka, wine, and beer. This is done in academia with students, so we have lots of alcohol. It can actually tell the difference between Coors and Stella. It can tell the difference between good milk and milk that's gone bad. It can tell the difference between water and very diluted milk and water. Don't ask me why we tested that one. It was a mistake. It was pretty gross. Okay. So if you've ever, actually, I'll tell you a very quick story. When we were bubbling these liquids, we wanted to filter it, get rid of all the gunk in the orange juice, the pulp or whatever, right, and just do juice, for instance. So we tried to filter milk. I don't know if you guys have ever, milk seems like a liquid, but it has a bunch of stuff in it, apparently. Yeah, and when you try and filter it, it's just gross. And yeah, so I just had buckets in this lab. And by the way, these labs are, clean rooms. This is like an auxiliary clean room, okay? But they're about 100 times cleaner than operating theaters, right? Extremely clean. There's beakers of milk, being filtered and stuff, and it was a Frankenstein. But anyway, not the point here. And also not the point is a gas sensor. Right? I want to make sure that you don't leave today thinking that you saw the future of gas sensing, because the takeaway message is much deeper than that, right? 3D nanosystem is a demonstration, it's a platform for what future computing systems can and have to look like if we really want to do something special moving forwards. So if you think about what's required, we know that we need energy efficient devices to overcome the power wall. And we can do that by leveraging these new technologies like carbon nanotubes for logic, RAM for memory, etc., which give us energy efficient devices. But we know that's not enough. because we have other challenges like the memory wall, the memory logic bandwidth wall. And to overcome that, we can leverage monolithic 3D integration to provide very dense interconnects between these layers of logic and memory, which are enabled by using these new devices to begin with. And if we want systems to do more than just compute on raw data, right? If we really want computing to interact in our lives in intimate different ways, then we need to bring sensing as close to the computing as possible, which again we can leverage with these new technologies, which can be used to make both great devices for computing, but also great sensing and sensors for all this new exciting functionality that a computer can have in it. And these are the main takeaways from this type of demonstration. Okay, so I'm going to wrap up the last kind of 2 minutes here by going over what's next, right? This is in academia, but when are you going to see a chip or buy a chip that you can program or use yourself, okay? So really excited. There's been all this work over the last couple of years across the entire system stack, getting to the point where carbon nanotubes are actually today being manufactured inside of commercial manufacturing to build these new monolithic 3D systems. And not just one instance, I'm going to give you 2 examples of how so, okay? So the first is in healthcare. So this is a very exciting project that we have that we're working on that's led by us here at MIT, as well as folks at Analog Devices that we work very closely with, as well as folks in Massachusetts General Hospital, one of the best clinical hospitals in the world. And the goal is to take this chip that has millions of gas sensors, instead of sensing unfiltered milk, can we actually detect bacteria that's inside of a patient, right? Can we actually do something clinically useful with it for a whole host of different applications? What we've actually done is actually gone one step further. Instead of sensing what's inside of your breath, instead we are smelling the breathing of bacteria. So bacteria are living and breathing cells just like us. In fact, when your shoes smell or you have bad breath or body odor or whatever, that's bacteria that's growing, that's giving off this smell. So in the clinic, they take these samples, your blood, sputum, which is your spit, urine, etc., and they culture them manually in petri dishes, and they manually look at them under microscopes, and it takes days to find a diagnosis. Have you ever gone to the doctors? Maybe you don't have to raise your hand, but I've been to the doctors, and they give you antibiotics, and they say if you don't feel better in 3 or 4 days, come back, give me a call. And the reason why they say that is because they don't know what bacteria is affecting you. It takes them about a week or so to get the exact bacteria and the strain of that organism to know exactly what antibiotic to give you. So they give you the most common one, and if it's not the right one, in a couple of days you still feel like crap, so they give you a different one, right? And for us, you're pretty healthy, it's not a big deal, but if you're in the hospital, you have a compromised immune system, you're already pretty sick, you have a compromised immune system, etc., every day matters big time. It's a big deal. So can we actually do this electronically? So we're actually smelling the breathing of these bacteria and can actually smell and differentiate bacteria after a couple of minutes, completely electronically, automatically now. Okay. Let me give you a second final example of more in the computing domain. That's healthcare. So this is in computing. So this is a program called 3D SoC. It's one of the largest programs run through DARPA, which is the one of the biggest agencies in DoD that sponsors research. As I mentioned, it's very, very large. I only give the value roughly, over 100 million to give you an idea of kind of the scope and how serious this work is now. And this is led by myself here at MIT with Nantha Chandrakostan, the Dean of our School of Engineering, my friends and actually past PhD advisors at Stanford University. And we're doing this at a foundry called Skywater Semiconductor. You probably haven't heard of Skywater, but I'm sure you've heard of Cypress Semiconductor. So Skywater was a subsidiary spin out from Cypress as a foundry arm, which is now completely private that we're working with. And the goal of this program is, you already know, is to take a 2D system like this today and transform it into a monolithic 3D chip, where we have carbon nanotubes for computing, ARM for memory. This is an actual picture of, we've built out this new kind of clean room where we're kind of doing this as a kind of add-on to the foundry, and we're actually building big industry standard wafers inside the foundry that look exactly like all the chips that I've been showing you today. This is actually a picture of the very first monolithic 3D wafer ever built in industry using layers of silicon, carbon nanotubes, and RM. So it's becoming a very real thing. So with that, let me wrap up. I hope I've been able to show you that while lots of people are talking about the end of computing, and particularly the end of hardware, I don't think that's the case. I think nanosystems give us a lot of exciting opportunities, and it's not just exciting opportunities, but we can do them today. So really appreciate your invitation to be here. It's always exciting to talk to folks. I'm a professor, so all I do is just talk, right? And so I love it. Appreciate you guys listening, and I'll stick around. I'm happy to kind of answer any questions and just chat a little bit. So thanks for your kind attention. I hope there's interest.
Yeah, thanks again for coming. The pizza did arrive on time, unlike lunch. It's Otto's Pizza, so it's good pizza. And we'll be moving over to the R&D Common in Stata again for that. And then afterward, you can feel free to stick around and do whatever you like, but we'll also be at 9 o'clock having a game night in the SIPB office, which is a tradition started by NPFOS. Right, and on Monday, if you guys are still here, you know, you are always welcome to come to the SIPB meeting,
Wow,
and
thank
then
you.
afterward,
No one's ever
hopefully
caught that
we'll have
before.
a big
Appreciate
food
it.
bob and, you know,
I
walk up
appreciate
the
it. Thank
entire
you.
space in Mary Chums.
No, I appreciate it. I
Mary
appreciate
Chums
it.
after a meeting
Oh, thank
instead
you.
of before. That's the
Question.
change.
So
Yeah, I
you
guess,
the
yeah, in recent years, it's always been after, I guess.
I mean,
Even the
the way,
most
the way,
modern
the way
processes
that
you have
modern
a
tradition works is
100%
meeting at 7:30. Someone says during the meeting we should have dinner.
yield. Yeah,
We
that's
waste an hour.
Okay.
We waste an hour trying to decide to go to dinner. We go to dinner, and it takes
for example,
forever.
I mean everyone has a certain level. Do you mean at the system level there's not that great performance or what?
So, in some places, you can do corrections. So, as
Mary Chums.
they do call and one as
Tomorrow's a Monday, and the week
Yeah.
of Tuesdays already happened,
Yeah, I mean, they-
because it
If you
ruined
look
my
at
plans for when I was going to take off freshman.
like an ALU, for instance.
Yeah.
They don't build 3 ALUs and hope one of them works. And then
Tomorrow,
just
we
use
can
the
get
other.
tomorrow.
If one transition to ALU doesn't work, then the ALU will give you the wrong result. So if you